There are so many things to do. No, it works. Okay. So basically, we missed the first part of the course, which was not very important. So, okay. And now we can start recording, watching the. Okay, this is more important. So I was saying, where should we study? Basically, the best suggestion is to take notes, just because there is not one single book which covers the whole class, the whole subject. And so I derived my slides from different books. I can give you some photocopies of those books. Well, I say Cedar Smith, this is a textbook for last year of electronics. It's a good starting point if you don't remember how many terminals has a transistor or things like that, okay? If you just want to remember the basics of electronics, and also for those of you that maybe are not familiar with some circuits, like differential amplified based on BJT, there may be people who don't remember this. Something about current mirrors, with or current mirror. So please, if you have problems, have a look on the Cedar Smith. Also, I ask everybody, if you have problems on some particular circuit, please stop me and let me know that you don't know something. I'm considering especially those students which are coming from abroad, okay? I know that people from Palermo should know many of these things, but some of you may not be familiar with those subjects. Please tell me now or never, I'll say. Because otherwise, when we go to the final exam, we may have very bad problems, okay? So let me know in advance that you have problems, in case I can give you some explanation on that. Okay, so apart from the Cedar Smith, most of the things I am covering, I took them from this Paul Young Electronic Communication Techniques. It's a bit hard to find. There is only one copy here in the library, but for some parts I can give you copies of this scanned pages of this book. Most of the course will be covered by this Kraus, Bosnian, and Raab solid-state radio engineering. It's a relatively old book, but it's simple. It's and it's really explaining the circuits. While most of the modern books are just saying blocks, but they don't say what is inside the blocks. Okay, but while here it shows you the circuits. About this book, I can say that if you have a look around and you know where, you can find it in PDF. So, okay, it's up to you to try to find it. Okay, let's go further. Now, this is very interesting. If you have a problem, I can give you a few pages of it again. Now, I don't remember what is mine. Okay, this is my email address in case you have problems. So giuseppe.lull@unipa.it. So you can send me an email or you can contact me through Teams if you have problems. You should be familiar with that. Now, what is next? Okay, if you want, we can start to talk about something more interesting. Like what? As I told you, the first subject that we'll study in this course has to do with the linear power supplies. What is a linear power supplies? Well, basically, linear power supplies is something, a box, which converts the AC voltage coming from the mains, so from the plug in the wall, the two holes that you find in the wall. Usually, those are 220 volts or 230 volts. When I say 230 volts, I mean the effective voltage, tensione efficace. Effective voltage means that the real peak value is 1.4 times higher. If you remember the relationship for a sinusoidal voltage between the peak voltage and the effective voltage, tensione efficace in Italian, is square root of 2, radice di 2. So you have to divide the peak voltage by 1.4, and you get the effective voltage. This means that the sinusoidal voltage at the input, I can do something like this. Let me see if I can do this, okay? You have here a sinusoidal voltage which goes up and down. And for this sinusoidal voltage, well, this is very bad sinusoidal voltage. Okay, let's do like this, okay. The peak voltage is 310 volts, more or less. If we consider the effective voltage, we go down to 230 volts. This is something that we must keep in mind because we are going to use it in a few moments. Okay, usually in this linear power supply, there is a transformer with a ratio between the primary and secondary windings of N1 to N2. And usually the number of coils, of turns, speed in the secondary is lower than the primary. Maybe you know that the output voltage will be decreased by the ratio N2 over N1. So if, for instance, if we have N2, which is half of the number of turns than N1, quindi su N2 ci sono metà spire che N1, the output voltage will be half of the input voltage. Okay? So in a transformer, the output voltage depends on the ratio between the secondary and the primary number of turns. And that's interesting because most of the time we are using a power supply for low voltage equipments like a cell phone. In a cell phone, we need basically 5 volts. So we must reduce the voltage from the mains down to something close to 5 volts. It's not exactly 5 volts, and that we'll see why. Okay. In this picture here, actually we have 3 main blocks. The 3 main blocks are a rectifier, a filter, and a regulator. These are the 3 parts which make a linear power supply. It's a power supply because it gives you a DC output voltage. So if we want a DC output which simulates in basically a battery, the battery is the ideal power supply. The problem is that the battery discharges after some time. Okay. So instead of using a battery and throwing it away, buying a new battery and so on, we prefer to have a DC output coming from the mains, so it will never finish. And we talk about a power supply every time that from the mains we get a DC output. But this DC output can be generated using only the first 2 blocks, rectifier and filter. We consider a linear power supply. We consider a linear power supply if we add the regulator. The regulator is a piece of electronics which has some feedback at inside it, which is used for stabilizing at a very high level the output voltage. Okay? So now what we are going to do is basically to have a look at the different blocks. And we'll see that if we just put a rectifier after the transformer, we have a voltage which will be unipolar. So it will be always positive, for instance, but we'll have a lot of variation. Then we add the filter, and we get the DC voltage, which is quite okay, but still some ripple, we call it, some variation. If we add the regulator, we get a perfect DC voltage, almost perfect. Then we'll see how we can characterize the system. In this slide, we have also 2 definitions. One is for the regulation in percentage, and the other one is about the ripple factor. What is regulation in percentage? We consider regulation as an indicator of the variation of the output voltage, so the variation of this DC output voltage, when we have no load and when we have a load applied at the output. For load, I mean a resistor, something which is draining current from the power supply. Okay, so if I consider that I'm going to, I don't know if this works. Let me show if it works. Fine. If I suppose that basically we will have a resistor placed here, something like this, okay? It's a touch screen. Okay, so we usually call it RL, load resistance. When we apply a load resistance to our power supply, we will see that there will be some current flowing through the resistor. Due to this current, usually the output voltage will go down, will reduce, because we are loading the power supply. So just to give an idea of how stable the power supply is, we define this regulation percentage, and we do this. We just measure the output voltage when there is no load, so that we output at open circuit without load. Then we put the maximum load for which the power supply has been designed. For instance, something which will drain 1 amp or 10 amps, something, depending on which are the characteristics that we declare for the power supply. And so in this case, the output voltage will go down. And we take the difference. So this is the output at the maximum load. We take the difference and we divide for the voltage at the worst case again. In this case, we see which is the percentage of variation between no load and maximum load. Actually, we may have chosen not V output max load, but V open circuit at the denominator. But if we consider the voltage at open circuit at the denominator, this variation will be smaller because the output voltage without the load is higher than when it is loaded. But just because we want to show which are the worst performances of our circuit, we decide to use the smaller number, which is the output at maximum load. Just to have an idea, we may design our circuit, for instance, for having a 12 volt. Oh, sorry, the pen is here. Okay. So, for instance, I decide with an open circuit voltage of 12 volt. Okay. Then I put a load, say drains 2 amps, I don't know, something, and I measure that the output voltage will go down to 10 volts. Okay? Divided by 10 volts, that is the minimum voltage. This makes what? 12 minus 10, 2 volts, divided by 10 is 20%. It's 0.2 or 20%. Okay? So we have a variation of 20%. If at the denominator I use the 12 instead of 10, this number could be smaller. But I want to know what is the performance in real operation. So in real operation, I will work probably at the maximum load. That's why I use the maximum the voltage at maximum load at the denominator. It's a definition. We can define as we want, but in this case, it's more convenient to define in this way. I can tell you, also for this simple example, I'm showing you that there are 2 possible definitions. One which looks better and one which looks worse. Probably when you buy something, the producer will show you the good values just because he has defined this performance in a way that is favorable to his product. But you must always ask what is the definition. Because if they just give you the number, you are not sure how they measured it. So if in the data sheet of good devices, they always tell you how the measurement was made. If you don't see this information, it means that they are trying to sell you something bad. Okay? This is something that you must be very careful when you look at the data sheet of some product. Okay? Most of the time, they are trying to fool you. Okay. Another interesting parameter is the ripple factor. What is the ripple factor? We will see in a short time that the output voltage of this power supply are not perfectly constant. But most of the time, you can find more or less an average voltage, which can be considered constant, but the real voltage will go up and down around this average voltage. So, we call DC output the average.
Professore?
Yes, please.
Mi scusi, non vediamo più le slide.
Non vedete più le slide? Ah, ok. Ok, ma da quanto tempo non vedete più le slide?
No, da circa 30 secondi.
30 secondi, no. Dopo non avete l'audio, non so. Ok, no, I'll do that. I'll fix it.
Grazie.
Prego. I pressed the escape probably. Okay, now, can you see them? Le vedete?
Yes.
Sì? Okay. Okay, no, please tell me when you don't see anything. Okay. So I was saying that what we'll find in a few moments is that the output voltage of a linear power supply has a fixed part, an average voltage, which we call DC output, and a ripple. Ripple, we mean the variation around this average voltage. So one way of defining this ripple factor that is a bit complicated, but we will see how it is made, it is calculated, is to give a ratio between, well, we have the denominator, we have, where is the laser pointer here? So the denominator, we take the average of the output voltage, while at denominator, we don't put just the amplitude of the ripple, but we put the root mean square value of the ripple. Why the root mean square? Because the root mean square is an indication of the power associated with the ripple. The root mean square is a definition of the effective voltage, for instance. And the effective voltage, again, is associated to the power, equivalent power of a signal. While if we put the ripple is just the amplitude peak to peak of the variation. And this variation may have different shapes. So if the shape changes, the ripple will change. While if you use the root mean square value, so that the power associated with the ripple, that's a more precise measurement of the ripple itself. But we will calculate this at the very end of this presentation, because it takes some time to calculate. I will show you just one example. Once you know how to do, if you have different cases, you know the steps for calculating it. It's just a matter of making some integrals, which is quite boring. Okay, so now the first block that we are considering. The first blocks have to do with the rectifier circuits. I told you that in each of these circuits, you see that there is always a transformer. So you can imagine that at the left side of the transformer, we have the mains voltage, 230 volts, AC, alternating current. Then on the secondary, on the right wing of the transformer, we have a reduced voltage. But it is still an AC voltage, so something which is positive, negative waves. I can schematize this, saying that I'm able to do this. Here you have a very large sinusoidal voltage. This is a sinusoid. Here you have a small sinusoidal voltage. Okay, something like this. But our equipments usually work with DC voltage. So a voltage which has always the same sign, it's positive for instance, but also the same value. So the first step that we have to do is try to convert a AC voltage into a DC voltage. How can we do that? Well, using diodes, basically. And here we have three possible configurations for diode rectifiers. If we have only one transformer and one diode, with this diode here, and you imagine, for instance, to have a load on the right, again, imagine you have a resistance here, something like that, okay? Place it here. In this case, what happens is that only the positive wave, the positive wave will bring the diode into the conduction. Because we have a positive on top and a negative voltage here. The diode will have a positive voltage on the anode, and so will conduct. This means that this positive wave will pass to the resistor. So on the resistor, you will have the positive half waves, the semi the positive of the input voltage. Okay, now then we will see better how it works. The negative waves will be stopped by the diode, because the diode will be backward biased, inversely biased, and so will stop the negative waves. This is what they call a half wave, because we are using only the positive half waves of the input signal. The output voltage will be a positive half wave and zero, positive half wave and zero, and so on. If we want to instead use both half waves, we must use a transformer which basically has two output windings which are connected in series. Usually this is called also center tap. Tap means connection. Tap is the rubinate, the system, the faucet, sometimes they call it, where the water is coming from. And so what happens here is that you will have a positive voltage with respect to the center tap when you have also negative voltage with respect to the center tap. So only one diode will conduct, for instance, the top diode, and the bottom diode will be open. And so you have the input half wave is transferred to the output. When the voltage reverses, you will have a positive on the bottom and a negative voltage on top. Only the bottom diode will conduct, not the top diode. The point is that this system, this circuit works fine. So now you basically have half a wave, and then half a wave again, and half a wave, and so on. So the output voltage is more similar to a DC voltage. It's still far from a DC voltage, but it is more similar. The point with this circuit is that you have basically two rectifiers which are separated. They just share one wire, have one wire in common. This means that the number of turns that you have on the secondary must be the same on both half windings. So if in the half wave you needed 10 coils, 10 turns for the secondary, here you need 10 plus 10, 20 coils. This means that you need 2 times the copper you needed for the secondary windings. And this is can be very expensive now that copper is very expensive. And also the transformer is heavy because it has a double winding for the secondary, okay? The circuit is nice because it can give you a better waveform than the half wave. But you need 2 diodes. But what is more expensive is that you need also the double copper on the secondary. Okay. Well, now the diodes are very cheap. They don't cost much because we are using semiconductor diodes, junction diodes. But you have to consider that in the past, each diode of this was an electronic tube, valve. So something which was very expensive. That is the reason why maybe this was not very popular. Most of the time people used in the past the half-wave rectifier. Now that the diodes are very cheap, we can also move to a different circuit, the full wave or Gratz bridge. Basically, the point with the great bridge is that, again, we can use the same secondary winding as we used for the half wave. So we don't need the center tap. We don't need to double the number of turns at the secondary. But we just increase the number of diodes. Using 4 diodes instead of 2, which now is very cheap because diodes are very cheap, we can have a full wave output after this circuit. Okay? There are some small defects that we will consider in a short time. Now we will see more in detail how the circuit works. Okay? Okay, just before we go further on, let me check the time. Okay. When we will explain the circuit, we must consider some parasitic effects that are there. We may decide or not to use them, to consider them. For instance, in our calculation, we may need to consider the resistance of the filament. Because here we have a transformer. A transformer is basically a combination of 2 coils, but the coil is made by a long piece of wire, and a long piece of wire has its own resistance. So we must consider some parasitic resistance in a model for this transformer. Usually we say that the transformer has no resistance, and we add an equivalent resistance in series at the output of the transformer. So it is easier to simulate. We have also the resistance of the diode. The diode, when it conducts, if you remember, has a characteristic which is, we say, there is a flat part and then there is something which has a slope. So the slope has to do with the internal resistance of the diode. But there is also a voltage drop that is the Ni voltage, the tensione al ginocchio, which is basically 0.6, 0.7 or more volts, which must be considered in our calculation. So I can tell you that most of the time we will certainly consider the diode, the voltage drop. Sometimes we consider the filament and the diode resistances. If you want to do some simple calculation, maybe we neglect them. We don't consider them, okay? So now we can see the different circuit. And for doing this, what I've done is using the software that I use, it is LT-SPICE. I've done a simulation of our circuits. So the top circuit is what we are considering. Just for simulation reasons, I have removed the transformer, and instead of the transformer, I've placed here an equivalent generator, which gives the voltage coming out from the secondary of the transformer, okay? So if, for instance, I had a particular reduction ratio between the input and the output, I suppose that here at the secondary I have 20 volts, 50 hertz, and 0 should be the starting time, if I don't remember, okay? So let's suppose that we have basically a secondary voltage of 20 volts. These 20 volts are the peak voltage. So if you want to calculate the effective voltage, you must divide by 1.4, and it will be something 14 volts of effective voltage, I don't remember, something like this. Then I used a diode, this is a standard diode, and I'm supposing that we have a load of 100 ohms. Okay? In this simulation on the right, I'm having a look at the voltage on node 1, which is the voltage on the sine wave generator, and node 2 in red, which is the voltage on the output resistance. If you see here, the input voltage, as we expected, is a 20 volts peak sinusoidal wave, the blue one, okay? Goes up and down. The timing scale, we can take it from the bottom. We have 40 milliseconds for 2 full waves. So 1 full wave is 20 milliseconds, which is 50 hertz. Okay, that's the net frequency. Then I have a look at what happens after the diode on the load resistance. If you see here, we have an almost perfect reproduction in red of the blue half wave, positive half wave. But when the half wave becomes negative, the diode opens, and so we have 0 voltage at the output. Okay? So the resistance will see only the positive half waves, but we'll see 0 during the negative half waves. If you look very carefully, and let me see if I can do this. You see here, there is a small difference between the blue and the red. What is this difference? This difference is due to the knee voltage, to the 0.7 volts drop across the diode. So when the diode is on, there are 0.7 volts between anode and cathode of the blue. And so we'll see them here. There are other slides where this effect will be expanded. Why will it be expanded? Basically, if you see here, in the red curve, we have 0.7 volts less than 20. So the peak voltage will be around 19.3. At this scale, you almost don't see the difference. But if the output voltage is lower, so if you have an output voltage which is closer to 0.7 volts, for instance, 3 volts, the 0.7 voltage will be a large percentage of error, okay? So every time you can, for instance, in this case, I can neglect the voltage drop of the diode. But if you have an output voltage which is much less, I must consider that the diode gives a voltage drop, okay? So every time we must consider if we can do or we can't do approximation. Another interesting thing to see is the current, the green line, is the current through the resistor R1. If you see here, the current through resistor R1 will follow precisely the voltage across the resistor. So you have you just divide the voltage by 100 ohms and you get to the current. It's perfectly the same. So the 0 milliamps is here. The peak voltage will be, okay, if the voltage across the resistor was 20 volts, divided by 100 ohms makes 200 milliamps. But here you see that we don't reach exactly 200 milliamps because the voltage on the resistor is not exactly 20 volts. This difference seems larger than here simply because the bottom scale is expanded. So, but the voltage is perfectly the same. Okay, so that's the output of a half-wave rectifier. Here in the red box, there is something that we must remember. Yes, the output voltage has a variation which has the same frequency as the input voltage. So you'll see 50 peaks per second as on the input voltage. We must consider this for later consideration that we'll make later. Another thing that we can calculate, for instance, is the average voltage of the average of the output voltage, what we would call VDC. How can we do that? We simply take the integral extended to one period of this particular shape, half wave and 0. If you do this integral, so you take the integral of Vt, the t over one period between 0 and t and divide by the periods itself, you will get V maximum divided by pi, p greater. So this means that the average voltage that we get at the output is something like 1/3 of the maximum voltage. Oh, sorry, for this one, of the maximum voltage. Again, we cannot certainly use this kind of voltage as a power supply for an equipment. If you try to send this voltage to an amplifier, for instance, what you will get is a very loud noise. You will hear the 50 Hz noise because the amplifier will amplify or will let you hear this kind of signal. I'm considering to use this rectifier as the supply voltage for an op pump, for instance. And if the op pump has no voltage at a certain point, the output will follow the same noise. Okay. And okay, this is the same as before, but here I have added two parasitic effects. So basically, I'm considering the diode drop, the voltage drop, but also the filament drop. So just because we have a resistance in the filament of the secondary winding of the transformer, if I want to keep into account the resistance in the secondary winding of the transformer, I have to put an equivalent resistance in series with the generator. So if you add the two effects, you will get this plot here. Let me see. Okay. Here we can see something interesting. Again, I'm plotting a voltage Vn on the node 1 and the voltage on the node 2. But while the node 2 is still the voltage on the output resistance, the node 1 is after the resistance, the filament resistance. So, okay, I changed also the voltage. Before it was 20 volts, now it's 5, it is 5, so it's easier to see the effect of this reduced voltage. And what I can see here, just look first at the blue line. The blue line has a negative peak voltage of -5, but has a positive peak voltage below 5. Why? Simply because we are measuring the voltage after the filament resistance. What happens is that during the positive peaks, the diode conducts. So there is a current in this loop. The current in the loop will give you a voltage drop across the resistance. That's why the output voltage will not reach 5 volts anymore. Only during the negative peak, when the diode is open, there will not be any drop across the filament resistance, and so we'll get again -5 volts. Okay, so what is the effect of considering the filament resistance? The effect is the voltage at the output of this real generator now, we'll say it is a real generator, will be lower than what we expected. It's no longer 5 volts, but is lower. What about the voltage across the resistance R1? Well, the voltage across the resistance R1 will be even lower, because there is also to add the drop across the diode. Okay? So this means that we started with a 5-volt peak voltage, and now we get a peak voltage, for instance, of 4 volts. Because we have to consider the drop across the diode, which is V gamma here, and the drop across the filament RF. You see this sort of yellow distance here from the peak, from 5 volt and the peak, okay? So that's the effect of considering both. Again, if we have very large voltages, we can neglect this effect. But if the output voltage is small, like in this case, we have an error of about 5%, it's 20–25%, depending on how we calculate it. So it cannot be neglected. Here, as I say, to be considered, the filament, the winding resistance, can we neglect it? But it depends. It depends also on the maximum current, because the higher the maximum current, the higher the voltage drop across the filament. Usually the voltage drop across the diode is constant, is more or less V gamma, even if the current goes high. But if the voltage drop across the filament depends on the output current, peak current, okay? Then again, we have to consider diode, resistance, here we neglected it, but the voltage drop across the diode must be considered for sure. Okay. Do we want to stop for 3 minutes? Okay, and then we'll keep it. We'll go on with the explanation. Okay, just 3 minutes stop.
Professore,
Ci sentiamo tra un poco, ok? Sì,
avevo una
vai.
domanda solo.
Deve parlare più o meno. Prego.
Ok, perché non ho capito perché è trascurabile la resistenza del filamento.
No, allora, diceva, why the filament winding is neglected? It depends on, on its value, and depends on the output current, and also it depends on the absolute voltage. I mean, in a case like this, where the input voltage is very high, the voltage drop due to the filament is small.
Okay,
But
okay.
in such a case, where you have, maybe you have a high current, and the output voltage is small, it's a good percentage of the output, okay?
Okay, I
Bene?
understand. Thanks.
Okay, right. Okay. Sorry, but it's very noisy here, so I had to increase the volume, okay.
Se dovessimo considerare quindi la resistenza del filamento del trasformatore, quindi del secondario, c'è l'RF e DROS.
Sì. R è stato filamento resistente. In genere il fabbricante dice quante cose oppure una camera quindi il trasformatore oppure se uno sa la sezione del tiro questo è il sì, assolutamente. Stiamo articolo a casa, diventato lavorativa, modificare appunto sparare. Poi alla fine no, io compro un booster non lo so. Just one moment, okay. I have to finish something. I'll remove the sharing, okay, for one moment.
Excuse me, teacher. We don't listen you because I have a microphone off.
Okay, now we should be ready to start again, hopefully. This one, okay. Can you see the presentation from home?
Yes.
I think so. Okay. Mettiamo il volume. Okay, now. So I think that we have seen most of this picture here. And I move to the next one. the full wave or center tap rectifier. Again, this is the schematic that we saw before. Now I simulating this schematic in this way. Basically, instead of considering two secondary windings, I placed two sinusoidal generators. If you see here, just because I want to simulate the same case as before, I had to place two sinusoidal generators of 20 volts. As I told you before, in the full wave rectifier, you need to place two identical secondary windings with the same number of turns. That's why the amount of copper that you need is doubled. And I simulate this using two sinusoidal power generators. I may have done it using the model of transformers, but in that case, probably we'll see something very strange. So I prefer to use adopt a very simplified version with only these two generators. Okay, I've done here exactly what I did before. So I am considering the two voltage generators of 20 volts without filament resistance in series. So in this case, I have this green voltage, which is the voltage on node 1. I use it also only the voltage on the V1 generator. The V2 generator gives a voltage which is the opposite of what we see here. So just to, in order not to make it very confusing. So the green is the voltage on node 1, and we see here that this voltage goes from 0 volts to 20 volts to minus 20 volts, and then up and down all the time, okay? Vn2 is the voltage on the resistance R1, is the voltage referred to ground. What I want to say is that when you do simulation, you always need to place a ground somewhere. Also before, you see, I placed the ground here. If you don't put a ground in a simulator, it will give you an error divided by 0 matrix and things like that. So you always need to fix a ground somewhere. Otherwise, the simulator will not start. Because all the voltages are calculated with reference to the ground point. Okay, so now I have basically this blue line, which represents the voltage across the resistor R1. If you see, now there are two half waves, both of which are positive. Okay. The situation has improved greatly if you consider what happened before. So during the negative voltage for the generator V1, in the past we had 0, now we have another positive peak. If you take the average voltage, and you do again using the integral, in this case you extend the integral to 1 cycle, which is 20 milliseconds, you can see that the average voltage has doubled. Before it was Vmax over pi, now it's 2 times Vmax over pi. That's very easy to understand. We simply have doubled the area of this curve here, so we have an average voltage which is 2 times. This output voltage is still pulsating, so there are pulses. It's not a perfectly DC voltage, but it's more similar to a perfect DC voltage than the situation that we had before. Okay. The other thing to consider is that now this output voltage has a variation with a frequency which is 2 times the F0, the network frequency. So the variation of this output voltage is 100 Hertz. Before it was 50 Hertz, now it is 100 Hertz. Because 2 times F0, the net frequency. This is interesting because having an output voltage with a variation which is faster than before means that when we want to filter it, we can use a capacitor which will be half of the previous case. Okay, more or less. So working at high frequency, usually gives you better performance than working at low frequency. Here, just the difference between 50 Hz variation and 100 Hz variation. When you will see what Professor Vitale does in its switching power supplies, in the switching power supplies, this variation will be over 100 kilohertz. So it will be very fast. And this means that for filtering, you can use small capacitors. That's one of the advantages of using the switching power supply. But we are the poor version, so we just use this kind of circuit. Okay. And I don't remember if the next picture I also plotted the current. Yes, I did it. Okay. Oh, in this case, just to see something a bit different, I plotted a situation where I have a lower voltage. Now the voltage is no longer 20 volts, but it's 5 volts. I removed the filament resistance, because otherwise it became too complicated. But I'm considering the voltage drop, V gamma, here. And I'm considering also the current. There's a mosquito here, sorry. I'm considering, no, forse metto la mascherina. Sorry. Okay, I'm considering the current flowing through the diodes. Okay? So in red is diode, the current through diode D1, and in blue is the current through diode D2. And what you see here is that during the first half cycle, we have current only through diode D1, then goes to 0. During the second half cycle, we have the current to the diode D2. The current flowing through R1 is the sum of those two currents. So follows the two peaks together, up and down. We saw it before. No, okay, we didn't see it before, but you can imagine that the current flowing through the resistance has the same shape as the voltage, just because the current in a resistor is the voltage divided by the resistance itself. Okay. Also, if you see the peak value of this current, it's 44 milliamps. 44 milliamps times 100 ohms makes 4.4 volts. So, why is 4.4 volts is the voltage over the resistance, which is 5 minus V gamma. In this case, V gamma is 0.6 volts, more or less. Okay, it means that this is a power diode, and so has a slower voltage drop. So more or less, it is working. And I think that next picture. So okay, this is more complicated. And just in order to underline which are the difference with the previous circuits, I'm using a low voltage. Now there's an error here. How can I also fix it? I'm using a low output voltage. So again, I'm using a 5 volts sinusoidal generator, and I'm using the Gratz bridge rectifier. Usually the Gratz bridge rectifier is designed like this, in a rotated square, let's say. Losang, I don't know in English how to say. If you don't remember how to place the diodes, you can remember that if this wire represents the positive output, it will hold the cathode of both diodes, which are connected to the two ends of the secondary winding. The other wire will give you the negative voltage, and is connected to the two anodes of these two diodes, which are connected to the two terminals of the windings. The same circuit can be plotted in this way. Again, you have this diode, D1, which was this one. D2 was this one, and this here. D3 was this one. D4 was that one. So, on the The wire connected to the cathode will give you the positive voltage. The wire connected to the anodes will give you the negative voltage. In this case, I placed the ground here. What happens in this case? How the circuit works? Well, let's start with a positive output voltage. So we have plus on top and minus on the bottom of the sinusoidal generator. This is our first case. I have to tell you something before. If you see here the green line, this green line represents the voltage across the sinusoidal generator. But I did not use here the voltage for one node, but here it is indicated V node 1, node 3. This means that the system is taking the difference between the node 1 and the node 3. Why? Simply because I didn't put the ground here, but I had to put the ground on this side. So if I have to put the ground on this side, the voltage over the two nodes, I have to say, I cannot consider the voltage of a single node to get the total voltage across the generator. One of the main differences between the Gratz bridge and the previous circuits is that it is not possible to have a common ground between the transformer and the output. If you look at the previous circuits, you see here, also this one. I placed the ground here, that means this wire, and so I have a common ground between the transformer and the output. For a single half-wave rectifier, I place the ground here, I have a common ground between the generator and the load. In the Gratz rectifier, it is not possible to have a ground on the load, which usually I prefer. I always want to have a ground on the load, and I cannot place a ground anywhere else. Okay? That's the reason why, if I want to know the voltage across the generator, I have to take the difference between node 1 and node 3. In terms of simulators, you just write V node 1, node 3. This means node 1 minus node 3. Okay? Okay, now I see what is the difference, the voltage coming from the generator. That means the secondary of the transformer. And that goes up to 5 and down to minus 5. Okay. If I have a look at the output voltage of, on R1, I see that there is a large voltage drop. I have to tell you that this 2V gamma here is a shift. They should go up. For some reason, the PowerPoint moved it down. I have to fix it later. I take a note. So, sorry, the pen. Okay, so I have to remember that there is an error here. Okay, that's for me. If you look at here, you see that there is a difference between 5 volts and 3 let's say 6, for instance. 1.4 volts of voltage drop. This voltage drop is given by 2V gamma. This means that in some way the current going to the resistance R1 is going through 2 different diodes. And we can see actually it is like this because, again, if we have a positive voltage on top and a negative voltage on the bottom of the sinusoidal generator, the current going to the load must follow this wire, then crosses diode D1, goes to the load here, crosses diode D4, and goes back to the generator. The other 2 diodes, D3 and D2, are reverse biased, so cannot conduct voltage. During the negative waves, we have a positive voltage on the bottom and a negative voltage on top of the generator. So the positive voltage will induce a current flowing through D2, goes here, crosses the resistor R1 and then closes to diode D3 and on. So in both cases, che è successo? No, funziona? No. Ricominciamo? No. Okay, no, I'll start again. So if we have a positive voltage on the bottom and negative on the top of V1, the current goes here, then goes through D2, sorry, this wire, the resistance here, and D3 up to the negative extreme, okay? So in both cases, what we see is that the current will flow always from the top to the bottom R1. This means that we have a positive voltage in both cases on the top terminal of R1. But the current will pass through D1 and D4 in the first case, D2 and D3 in the other case. In both cases, we have 2 voltage drops on the diode. And this means that we get V gamma voltage drop. That's why the peak voltage on the output is not 5, but is 5 minus 2 V gamma. Okay? It's smaller. It's written here. During input positive half wave, D1 and D4 conduct. During input negative half wave, D2 and D3 conduct. I forgot, it was already there, but okay. Anyway, these slides have to be used for, are optimized for you. I hope that you can follow the different concept, and then when you have to remember, everything is written more or less there, or you can take notes. Okay, here again, in this box on the bottom, there is also another consideration. I already told you that in this circuit, you have a double diode voltage drop, 2 V gammas, and there is no common ground with the source. That's something that I already told you. This means that the Gretz bridge is nice. It's very useful because it's using only the minimum amount of copper at the secondary winding, but you must accept the double voltage drop. If the output voltage is small, this error can be very large, and you have to consider it. If we are using a high voltage, you can neglect, again, this double voltage, this 1 volt voltage drop. Okay. There is also something that here is more evident than in the previous slides. The phenomenon that I'm going to talk about is also in the other rectifiers, but here, just due to the double voltage drop, is more evident. Let's zoom this part of the waves, and that is this part here. If you see the voltage on the output resistor, it is not exactly given by 2 half waves. There is a flat zone here. So there is a half wave, then a time during which the voltage is 0, and then it goes up again, and is a bit more zoomed here. Why is that? That is due to the fact that if the input voltage does not reach at least 2 V gammas, the 2 diodes cannot start to conduct. If you see here, 2 V gammas, the minimum value for 2 V gammas is around 1.2 volts. So if the green line does not reach 1.2 volts here, the blue line cannot move from 0. And that's something that here is more evident because you have to wait for 2 V gammas. In the previous circuit, you had to wait for 1 V gamma. So if I go back to this one, wave, okay, I should see here that I cannot zoom more than that. That green and the blue line are not perfectly overlapped. I used a very thick line, but the line is very thick, so you cannot see that here is flat. But if you use a larger voltage drop, like 1.2, it becomes more evident. Also with the small voltages, okay? So that's something that we may consider also during the design of what is coming next. Do you have any question about this, or I go further on? You can also ask me things later. Not a problem. Okay, now I go back to the previous case. Let's start again with the half-wave rectifier. Now I add something, a capacitive filter. Because we have seen that with the half-wave rectifier, I go back one moment. The output of a half-wave rectifier is more or less like this, the red line. And we don't like this. This is not a perfect DC. It's far from a perfect DC output voltage. So we must put a filter, basically a sort of low-pass filter, and we can do that adding a capacitance, a large capacitance. You see here, I'm using 1,000 microfarads. Don't be worried by the fact that there is not the F is not there. This is the simulator. He knows that capacitance are in farad, so it doesn't put microfarad, it just puts micro. Okay. The same as the resistance. You will never see 100 ohms. It's useless. Resistors are in ohms, so it just says 100. Okay. Okay, now this may look a bit complicated, but it is not so. What I simulated here again is secondary of a transformer. We have 15 minutes left. So 5 volts. I use low voltage, so all the defects will be very enhanced, evident. 50 Hz, okay. I neglected the filament resistance. I put the diode R1 and the capacitance R1, C1. And I plotted what? Green is the voltage here. Blue is the voltage at the output. R1 and C1 are in parallel. So we just need one voltage. And here I plotted in red the current through diode 1. But I also plotted the current through the capacitor C1. Okay? I did not plot the current through resistance R1 because, again, the current through R1 has the same shape as the voltage, which is blue. Just, it's a matter of scale. The current is proportional in a resistance to the voltage. So the shape of the current is, again, like this blue. While the currents in the diode and the capacitor are quite interesting. I could say that basically the shape of the current through the diode and through the capacitor, if you see, is the same. The difference between the current in the diode and the current in the capacitor is the current in the resistor. If you see the voltage in the resistor, you can understand that basically this current is almost constant. There is a big improvement in the shape of the voltage across the resistor just because we added the capacitor. Now the current in the voltage in the resistor and the current in the resistor is almost perfect. There is still some ripple, but it's much better than it was before without the capacitor. Okay. So we can say that there is just a small difference between the current and the capacitor and then the resistor, and the difference is almost a constant. It's the current in the resistor, in the reset. The difference between the current and the capacitor and the current and the diode is the current in the resistor, which is almost constant. Okay, I got confused. We see that there are peaks of current in the diodes and in the capacitor. There is a big peak at the beginning. Why that big peak? Because in my simulation, I supposed that the capacitor was discharged at the beginning. So at the beginning, the capacitor has 0 volts. When the first sinusoidal loop starts, much zoom, okay. When we have the first sinusoidal wave, just because the capacitor has 0 volts, there will be a large peak of current to charge the capacitor, which tries to follow the voltage at the input. You see that the blue line, which is also the voltage on the capacitor, is following almost perfectly the green line. So the capacitor at the beginning was discharged. 0 volts is the blue line. And the green line goes up, and the capacitor tries to follow this line. In order to charge the capacitor at the same voltage as the input, we need a very large current. That's the reason why we have such a large voltage peak, current peak, sorry. Well, when the voltage reaches, at the zoom, the peak, the input voltage, the capacitor has reached its peak. Again, the voltage in the capacitor is 0.7 volts lower than the peak, because we have the voltage drop on the diode. Well, what happens next is that the input voltage goes down, but the capacitor is already charged. So if the capacitor wants to discharge in order to follow the input voltage, it should discharge through the diode, but the diode is open because it does not allow a current to go from the cathode to the anode. So from this point here, the voltage on the capacitor is higher than the input voltage. Okay? So at the beginning, the capacitor follows the input voltage. When the input voltage goes down, the capacitor will discharge through the diode, but the diode opens, and bye-bye. The capacitor cannot discharge through the diode. It can discharge only through the resistance R1. Okay? So what we see here is an exponential discharge with a time constant given by C1 R1. That is written here. So the capacitor charges following the input voltage because it's charged through the 1. But when the 1 opens, the capacitor can discharge only through R1. This gives, we can also say, an abrupt change, a strong change between the charging time constant and discharging time constant. The charging time constant is basically given by the dynamic resistance of the diode 1, which charges the capacitor. When the diode opens, the discharge constant is given by C1 and the resistance which the capacitor sees, that is R1. So it is much lower. You see this? What happens here? Here, the capacitor has discharged a bit. When the input voltage is higher than 0.7 volts, the actual voltage on the capacitor, the diode opens, conducts again, and so we have this peak current here that is going to recharge the capacitor and bring the voltage on the capacitor up to the peak again. You see? Then the 10 voltage goes down, the diode opens, and we have the discharge of the capacitor through the diode. To the resistance, okay? If you see, basically the peak current and the diode, the peak current and the capacitor are almost the same. The average current to the resistor is much lower. Well, actually we can see the current through the resistance. Look at this picture. See that during the discharge, we have this current that is a bit below 0 amps. It's a negative current, meaning that it's a current coming out of the capacitor. Because usually, the current in the plots, the current going into the capacitor is positive, the current going out is negative. Also, this current is almost constant. Why? Because the voltage across the capacitor is almost constant. There is a very small variation. It's a small variation, but in this scale, which is very compressed, you can almost see the difference. You see that there is only a very small reduction in the current here. Okay. Because the current now is going out of the capacitor and going to this is the plot of the current in the capacitor, IC1. The current is coming out of the capacitor, so it is represented as a negative value. Okay? Pardon?
Is it flowing through the resistance?
Yes, in this way, through the resistance. Okay. So the capacitor is charging this way, and it's a positive current, peak current, and is discharging this way. The diode. Okay. Yeah, everything is written here. In this case, just because we are going to move to the next picture, I pointed out that, again, the ripple frequency is the same as F0, F the frequency of the input. This is a half-wave rectifier. We remember that we have a variation, a pulse of current, a pulse of voltage, also every input cycle, because only the positive half wave give a contribution to charging the capacitor. So, for instance, here I have 4 ripple periods in 80 milliseconds. That's why I placed this arrow here. In the next picture, this number will be 40. Now we'll see. This is the full wave, the center tap circuit. What happens here? Again, here I placed 2 generators, 2 diodes. Here we have a common ground, so we are lucky in this case. But when I look at the, this is okay. Once we know how the world works, I only placed here the current through the capacitor. If you look at the current through the capacitor, you see that apart from the initial peak, because the capacitor again is discharged, you have a peak of current at the beginning, okay? And then at the peak of the input voltage, a negative peak of the input voltage. Why? Simply because this full wave rectifier is using also the negative peak for charging the capacitor. So when there is a positive peak of the input voltage, you have again a peak in the capacitor current, is charged again. When there is a negative peak, the capacitor is charged again, because we are using this other path. The first time the current goes through diode D1, and we have the first peak here. During the negative peak of the input, the current goes this way, and we have again a charge peak for the capacitor. Positive peak D1, C1, we have this peak here. Negative wave, we have the path through D2, and we are charging C1 again. Okay? This means that now we have 4 variations, 4 peak of currents in 40 milliseconds. And actually, the frequency of the ripple, the frequency of the peak is 2 times F0. But that is something that we already saw. If we go back to the circuit without capacitive filter, I go back where? Here. You already saw that the voltage on the diode, on the resistor, and on the capacitor was going up and down 2 times per each cycle. Just because this diode D2 in some way is mirroring the negative wave into a positive wave. It's reflecting the wave. Okay. If we compare this picture to the previous picture, so there's a full wave rectifier with a half wave rectifier, we can actually consider that we had a sort of reduction to half of the ripple amplitude. Because in the previous circuit, which had only 1 diode, the capacitor was discharging from this value down to here. Now, instead, during the negative peak, we have also recharge of the capacitor. So the time that the capacitor has to discharge is half than the previous case. Now, if I go back, the point is that the scale are different. But if you consider that this picture here has a ripple with a scale which goes from 5 to -5, this picture is much larger. but the ripple seems to be the same. No, it's not the same. It's half than before. Okay. If I consider a circuit like this in the previous case, I can use the pen. The capacitor will discharge from here. Oh, where is the pen? Pen. Okay. From here to here, and I to full charge. Okay. While in this case, just at half of the time, say after 10 milliseconds, there is a new pulse of current which charges again the capacitor. When we will develop a formula for this variation, then we will try to calculate this ripple. We'll see that the frequency of the ripple is on the denominator of the amplitude. So if we have the frequency which is 2 times, the ripple is half. And that's more or less what we can see here. Okay. Okay. These are some definitions that will be used in a short time, but not now, for trying to calculate just the amount of this ripple. Basically, what we'll consider is this. We have input voltage, which is the blue line. The output voltage is the green line. Here again, okay. We can consider an average output voltage, which is called the VDC, or V with top line. That's the average. And we mean as a V ripple the peak-to-peak amplitude of the green line. So we can say that actually the output voltage, the green voltage, is given by the sum of the DC contribution plus the ripple. Okay? If we consider that the ripple is a wave which has a positive and negative peak, if we sum the two voltages, we get to the green line. So we can study, if it is possible, effect superposition theory, in the superposition of the effect, we can study the DC contribution and the ripple contribution, if it is possible. Okay? Now it's time to close. We had enough for today, and I think that we should meet again on Thursday. Okay? I want to tell you that probably sometime we will swap the lesson with Professor Vitale. Just because Professor Vitale is Thursday and Friday at 8 o'clock in the morning, and I am at 12. Maybe at some time we will invert, okay? But still we have not decided. Just some, if he's more busy or I'm more busy, then we will decide. Okay, so, yes, I just adjust something and then I'll put them on the, I will place them on the same channel in the file tab. There's a tab file, I'll put them there, okay? Okay, so bye-bye to everybody who is attending from home, okay? See you on Thursday. So it's very noisy here. Bye-bye.
Arrivederci.
Arrivederci. Bye-bye.
Arrivederci.